Right, this next parametric equation example deals with trig functions. Here I've got x equals 3 cosine t, y equals 3 sine t, and my t values range from 0 to 2 pi. Just some ideas here to lay down a foundation. The t values, because they are the inputs of trig functions, actually represent angles in this case, which is a nice way to represent this. Some people would put thetas in here. I like t's to keep this consistent. But the t value running from 0 to 2 pi, this could be any angle measure, but we typically use radians here. Okay, so now first thing I want to do is set up my xy table, txy table to get some values. And I'm not going to go too crazy with these. I really just want to get a feel for what's going on here. So the t values, well, again, t ranges from 0 to 2 pi. So what are some reasonable values for t? Well, maybe 0, multiples of pi, maybe pi over 2, maybe pi, maybe 3 pi over 2, and 2 pi. That might be kind of nice. That gets me all of my axes, right? My 0, my pi over 2, pi, 3 pi over 2, my arm doesn't go that way, 2 pi on the other side. So that gives me my coordinate axes. The x value then, corresponding x value, if I take 3 times the cosine of 0, well, if you remember, cosine of 0 is 1, so this would give me a value of 3, right, 3 times 1. If I do pi over 2 for the same x, right, 3 times cosine of pi over 2, cosine of pi over 2 is 0, so this would be 3 times 0, which is 0. If I do pi, I get 3 times the cosine of pi. Well, cosine is at -1 at pi. Cosine of pi is -1, so this would be -3. The way I'm remembering these is I just remember my graph of the cosine. This is how I personally do it. Pi being halfway across, 2 pi being all the way across. So the cosine starts at 1, goes down to 0, right? Cosine pi over 2 is 0. Cosine of pi is -1. And it comes back up to 3 pi over 2. 3 cosine 3 pi over 2. Well, the cosine of 3 pi over 2 is 0 again. And then 2 pi, 3 cosine of 2 pi. Well, 2 pi is up at 1, so 1 times 3 is 3. All right, so I've got that pattern, 3, 0, -3, 0, 3. Then the y values, correspondingly, you get 3 times the sine of 0. Now the sine starts at 0, goes up, down, and back up. This is pi, this is 2 pi, here's 3 pi over 2, and here's pi over 2. So you can get an idea of where those points are. I just chose easy ones, right? No 45s or 30s, all 90-degree multiples. So 0, sine of 0 is 0, so that's 0. 3 sine pi over 2, if I do pi over 2, that'd be 1. 3 times 1 is 3. 3 sine of pi. Pi is back down to 0, so 3 times 0 is 0. 3 sine of 3 pi over 2. The sine of 3 pi over 2 is -1. -1 times 3 is -3. And then finally 3 times the sine of 2 pi. Sine of 2 pi is 0. 3 times 0 is 0. And so I can plot all of those, or at least list them out: 0, 3, 0, -3, and 0. All right, so I've got all my points on here. Now I'm going to erase all my work in finding those values and then just go ahead and plot those 5 points. Okay, and now I need my graph. Basically, it's going to extend to 3 in every direction, right? -3 to 3. Maybe I'll just plot it to 4 so I know I have enough. So 1, 2, 3, 4, 1, 2, 3, 4. 1, 2, 3, 4. And 1, 2, 3, 4. Okay, that's good. So 3, 0 is my first point. I go over 3 up 0. Then I need 0, 3, so over 0 up 3. All right, so we started to the right, go up. Then negative 3, 0 is left 3. And then 0, negative 3 is down 3. And then 3, 0 is back over to the beginning. Well, what does this look like it's tracing out? Could it be a circle? Possible. Could it be a square, kind of on an angle? Possibly. Because of the nice smoothness of these functions, cosine and sine, I'm guessing it's a circle, and it is going to end up being a circle. If we plotted more points in between, like on a 45-degree angle, like pi over 4, we might be able to get a better feel for what that's going to do. But in our case here, it is indeed going to be a circle. See if I can get a somewhat decent graph. It's a little bit pointy on the ends, but close enough. And then I want the orientation. Oh, guess what I did? I put that at 4, didn't I? That would explain why that looks a little lopsided to me. That should be a negative 3, not a negative 4. Aha, right there. Okay, I don't know if that fixed it or not, but still looks better. All right, so basically the orientation is going clockwise, counterclockwise, sorry, around the circle. And so there's my orientation, started over on the right and wrapped itself around one full circumference. So that's pretty cool. Works out. The graph of this is a circle of radius 3 centered at the origin. So center at 0, 0. And then just to get the rectangular equation, that we can verify this using a rectangular equation. One thing I do know, now this is very hard to solve to get a rectangular equation out of, right? In the past, we've solved using, like, solving one equation for t and then plugging it back into the other equation. This one's very hard to work with because if you solve for t, you're going to end up with inverse trig functions, and then you have to put those into the other function and try to work that out. It becomes kind of a mess. It can be done, but you have to be very careful of your domain because the domain of the inverse trig functions is, you know, a little bit weird. We don't get all these points. If we do that, we have to be careful there. So there's some other tricky shortcuts. You have to be a little bit clever to do some of these. A lot of times you can use the trig identities to make this work out. Okay, so what I'm going to do here is I'm going to use the trig identity, the Pythagorean identity. Sine squared theta plus cosine squared theta equals 1. We know that that trig identity is always true, okay? It's the Pythagorean identity. There's lots of identities that are always true. Your half angle, double angle identities, your reciprocal identities, quotient identities, all those things are always true, and sometimes they can help us. Here I know that sine squared plus cosine squared is equal to 1. That's a given, okay? Here, in these equations, if I solve for cosine of t, I'd be dividing both sides by 3, so I know that cosine of t is equal to x over 3, and I know that the sine of t is equal to y over 3, right? I divide out the 3 on both sides of each of those equations. What's interesting is if I were to plug these in, so instead of cosine t, cosine theta, that's fine. It doesn't matter the variable. So the sine squared of t plus the cosine squared of t is equal to 1. The variable is arbitrary. And then I can replace the sine and the cosine with these expressions. So this is y over 3 quantity squared, x over 3 quantity squared equals 1. And then if I were to maybe rearrange those and expand a little bit, this could be, I could actually write this term first. Let's do x squared over 9 plus y squared over 9 is equal to 1. And then this actually looks a lot like the equation of an ellipse with major and minor axes of 3, right? 3 units, and so that's actually true. This is an ellipse where both the major and the minor axes are the same. Well, what do we call that? A circle. How do we verify that? Multiply both sides of this equation by 9. And what will we get? We'll get x squared plus y squared equals 9. Very cool. That's the equation of a circle centered at the origin with radius of 3, square root of 9. Okay? We've seen that before. So that kind of verifies that this combination does give us the equation of a circle radius 3, which is what we plotted anyway. But at least that verifies that it wasn't actually a box or something, a square going around with corners or something weird. It did actually trace out that circle. Okay, so what else is interesting about this? Another thing that's interesting, and of course I could use my graphing utility to do this again. It wouldn't be any different than what you've seen with the parabola in a previous video. We just do x1 is 3 cosine t, y1 is 3 sine t, and restrict your t from 0 to 2 pi, and you can make that work out. I won't go through the details of that again. But what is neat about this is that you can very easily plot the graph or come up with a parametric equation for a circle of any radius centered at the origin. All you really need to do is change the multiple, the coefficient. If I wanted a circle of radius 10, I just put a 10 there and a 10 there. If I wanted a circle of radius 0.5, I put a 0.5 there and a 0.5 there. If I wanted an ellipse whose major axis was in the x direction, maybe 2 units from the center to the vertex, and whose minor axis was 1 unit, then I put a 2 and a 1 in there. Okay, so an ellipse is actually the same combination, you just changed the coefficient to match what the major and minor axes are. It's a very quick change and very convenient way to represent an ellipse. So in other words, if I wanted to plot, let's say, an ellipse that was kind of oriented vertically here, and let's say this went from 5 to -5 and 2 to -2 in the x direction, then I could represent that using parametric equations. Of course, the orientation has to be correct. If the orientation is wrong, I may have to do something weird like just change the sign on the cosine or put a shift in the angle there, a phase shift or something to make everything work out. But if I want just the graph and not worried about the orientation, I just change the coefficients here. And what I would end up with, the x direction is 2, so I'd have x equals 2 cosine t, and y equals, well, that's 5 sine t. It essentially stretches the circle out 5 units or 5 times in one direction and 2 times in the other direction, sort of. And then, of course, you're limiting your t values from 0 to 2 pi. All right, so it's kind of neat. You can make adjustments to these equations, and it's very quick. I also then can immediately come up with the corresponding rectangular form. Again, the same sort of idea. You use the Pythagorean identity, substitute stuff in, and what you would end up with, of course, is x squared over 4 plus y squared over 25 is equal to 1. It would be very similar to what we had before, where we had just the pair of 9s there. Now we would have 4 and 25, because when I solve for those, I divide out the 2 and divide out the 5 and then square them. So it works out very nicely that way.